So we would like to discuss linearly independent set of vectors in this class, and then linearly dependent set of vectors also. So we have already seen the concept of linear combination, LC. A linear combination of vectors, basically a finite number of vectors are picked from a vector space, and that we have seen that it's of the form some summation aivi, summation running through I to I equal to 1 to n. So a set of n vectors, say s is equal to v1 v2 dot 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 vn, are said to be linearly independent if no non-trivial linear combination of vectors in S gives rise to the null vector. So in most of the books, the Western books, they first define linearly dependent vectors, but we are doing the other way around. We are first defining linearly independent. That is, if you take the expression of the form alpha 1 v1 plus alpha 2 v2 so on up to alpha and vn equal to the null vector, then this kind of equation is possible if and only if uh, every scalar is zero. If such a situation arises, then the n vectors are linearly independent. So even if we have some non-zero scalars, then what happens is that there is a relation between the given vectors, and therefore they are not linearly dependent. They are not linearly independent. Sorry. So even if there is one scalar alpha I is non-zero also, we should say that it is uh, linearly dependent set. So this also gives us a hint that any singleton set of a non-zero vector is always considered as linearly dependent. Yeah, because if I have the vector as non-zero, then it can be rendered zero only when I take the scalar zero. Otherwise, you cannot, and so, therefore this is a fact. And any set S naught of this form is linearly dependent if it is not linearly independent, I should have said. Sorry. If it is not linearly, say, independent. Yeah. A set is called linearly dependent if it is not linearly independent. So we would like to reword it in another way, the linearly dependent set. There are two ways, in fact. If we have, I have shown this. I'll write in another color. Maybe if you have these k vectors joined by this kind of a equation, a1 w1 plus a2 w2 so on up to ak wk is equal to 0 with at least some of them non-zero. So if we are able to get the zero vector on the right side as a linear combination, a non-trivial linear combination, then it is linearly dependent. That is one rewording. Another rewording is here. I'll take a highlighter again. So yeah, another rewording is the following. Let S be the set v1, v2 up to vt. Further, we assume that it's an ordered set, which is very clear by the indexing. So it is linearly dependent if and only if any vk such that k is satisfying 1 less than k less than or equal to t, can be written, that vk vector can be written as a linear combination of the preceding k minus 1 vectors. So this can be rigorously proven that whenever we have a linearly dependent set, then some vk can be written as a linear combination of the preceding k minus 1 vectors. So this actually gives you some kind of a hint what you learned in the lower classes. In fact, I want to say something more. If you confine to, let us confine to finite dimensional space, vector spaces, more concretely Rn, then any set of n vectors can will be linearly dependent. This is a convenient way for people to even write algorithms. If and only if the matrix made out of these n vectors, say this is the first column vector, this is second column vector, and I'm picking n vectors in n dimensional space. So this matrix is clearly an n cross n matrix. So this matrix is made by stacking the column vectors in this way. If and only if for a equal to this, determinant of a equal to 0. So this is although one can rigorously prove this also, by hand waving also I can say what exactly happens. So let me write let's say an example for that. Let v1 be 113, v2 be 315, v3 be 226. You see, I deliberately took something in this fashion. 315, 226. So by the reworded definition earlier, we can see that the third vector is a combination of the other vectors in such a way that some alpha 1 v1 plus alpha 2 v2 is equal to v3. Can I say this? Because you see that the third vector is twice the first vector. So you can put alpha 2 is equal to 0, alpha 1 as 2, and we get this, which means that there are two ways of thinking about it. You can find rank of A. Let's say A is representing those three vectors. Rank of A is clearly not a full rank. It is 2, not 3. And so determinant of A is equal to 0. That's one way of thinking. Other way of thinking is that this equation that I wrote here can be rewritten as alpha 1 v1 plus 0 times v2 minus 1 times v3 is the 0 vector. So again, I can get a linear combination of v1, v2, v3, not all scalars 0, such that we could express the 0 vector as a linear combination. And therefore, that also, by that definition also, these three vectors represent a linearly dependent set. And so this is a nice way of checking if given vectors are linearly dependent or linearly independent. Now, one can easily say that if if we stack the vectors and say that a rank of A is full rank. In fact, I'm always taking A to be a square matrix. Then definitely determinant is not equal to 0, and the given vectors are linearly independent. So with this small example, we could see that how one can check by matrices. That's a matrix connection also. But in general, how do we see if a given set of vectors in, let's say for simplicity, R3 is linearly independent? This is what I've been using in class. Li for linearly independent, or LD for linearly dependent. So how does one check? Is directly go by this matrix, or in other words, check the rank of the matrix formed. But then one can even say something more. Uh, given any uh, given any set of 4 vectors in R3, has to be linearly dependent. The reason being that uh, any vector in R3 can be generated by three linearly independent vectors. Of the form 1 0 0 0 1 0 0 0 1, or more generally any, this is a standard basis, but any 3 linearly independent vectors can span the whole of R3. And so if without loss of generality, if I assume that vector 1, vector 2, vector 3 are linearly independent, then the Li, if I assume, then the fourth vector becomes a linear combination of the first three. But if we don't, if you don't get that assumption true, that is already within V1, V2, V3, we find some relation among them, which means that they are already linearly dependent. So in any case, this set of 4 vectors, I started with any set of 4 vectors, right? So this set of 4 vectors, let's say the fourth vector v4. So this set of 4 vectors v1, v2, v3, v4 becomes LD. So that's a simple observation. So now, because I dryly defined linearly independent set and linearly dependent set, let's do some examples. Check if S is equal to 3, 1, 5, 2, 2, 6, 1, 1, 5 is linearly independent or not. So we can put them in. I'll write the third vector in the first row because I want to do the row operations. Right? Let A be the matrix formed. Now in this case, unlike the proof that I showed earlier, I am not stacking them as columns, but I'm stacking them as rows. So both are okay. Both can be done. So A is this. So now what I'll do, R2 can be replaced as R2 minus 2R1. R3 can be replaced as R3 minus 3R1. So that this becomes equivalent to another matrix 1, 1, 5, 0, 0, 6 minus 10 is minus 4, 0, minus 2, 5 minus 15 is minus 10. Now, even if before writing the whole row echelon form, we can expand by this row and see what is happening here. The determinant is plus 4 into minus 2. So minus 8 is the determinant. Therefore, clearly A has full rank. You cannot get one full row 0. So clearly rank of A is 3 and determinant of A is non-zero. It's actually minus 8. And therefore, you are unable to find a relation between any two vectors. So by the reworded definition of linearly dependent, none of these vectors are linearly dependent to the preceding ones. Therefore, they are all linearly independent, and therefore this is true. It is indeed linearly independent, right? So now one could even look at linearly independent sets in infinite dimensional space. Remember, I said that space of all. I gave this example of the space of all continuous functions on some interval on the real line or the extended line, real line. So I would consider the set S as part of this space, x sine x cos x. So this fx is equal to x is one function, fx is equal to sine x is one function, fx is equal to cos x is one function. So is the set linearly independent or not? So because this is infinite dimensional, I won't go by the matrix form, but what one can argue is no non-trivial linear combination of the elements of S can give the zero vector. I used to say null vector for 0 bar there. I used to write 0 bar. Here I would say the zero vector is like f I is identically 0 for all x. F is equal to 0. That's the constant function fx is equal to 0 is the uh, zero vector in this space. So can you get 0 by any linear combination of this unless you write the scalar 0? The only way to get 0 is by using a1 equal to a2 equal to a3 is equal to 0. That is a1 times x plus a2 times sine x plus a3 times cos x will become this zero function. I'll again use maybe will become the zero vector if and only if a1 equal to a2 equal to 0, a is equal to a3 is equal to 0. Hence S is a linearly independent set. So I'll end the class here.